In section 6.2, we'll be looking at some more trigonometric equations and how we can, in most cases, use identities in order to be able to rewrite the equations so that we can then use appropriate algebraic technique to solve these trigonometric equations. In general, we'll say, well, if we could be able to factor the equation, we've already seen examples like that in section 6.1. If we can express it as a product of factors equal to 0, then we can set each factor equal to 0. And an example like that where we could factor to solve the equation, maybe could be, let's say something like sine x cosine x plus sine x is equal to 0. An equation like this could have showed up in the previous section. We would have factored out the common factor of sine x, for instance, and then we have a product of factors equal to 0. Then we can just set each of those factors equal to 0 and solve those basic trigonometric equations then. Remember, it's something like the sine of x is equal to 0. I would envision the unit circle and say, well, the sine of x in the unit circle is the y coordinate, and the y coordinate is 0 here and here, so I get solutions where x is equal to 0 and x is equal to, let's say, pi. I'll write the answers in radians. So those are solutions to this equation. And then this is the cosine x is equal to -1. In the unit circle, the cosine is the x coordinate, and the x coordinate would exist right here. So here again we get that x is equal to pi, but we already had that as a solution. So we're done. So the solutions to the original equation are 0 and pi. So this would be a type of example we would have seen in section 6.1 where we could have used factoring as a strategy because we could have a product of factors equal to 0. Okay. All right. So moving into section 6.2 then, is if we can't apply that strategy there, there it goes. Okay. Right. If we can't apply that strategy, but suppose that we have more than one trigonometric function in the equation, like the equation that I just had up there had a sine function and a cosine function in it. Okay. But we were able to solve it by simply factoring. In general, if we have more than one trigonometric function in an equation, we would want to use identities then in order to express all of those trigonometric functions, in fact, in terms of the same trigonometric function. So our goal is going to be, can we get all of the terms that are trigonometric, all the trigonometric terms, can we get them all to be with respect to the same trigonometric function, like maybe all the terms have cosines in them, for example, and the same argument, like let's say that all of them have the argument theta in them, for example, as opposed to having a term with a theta in it and another term with a 2 theta and another term with a 3 theta or something like that. If we can get all of them to have the exact same argument and the exact same trigonometric function, okay, then we'll see if we can apply algebraic techniques to be able to solve. Okay. So in this section, we'll mostly be looking at examples whereby we'll be using identities, as we've been studying so far throughout recent chapters. All right. We'll be using identities in order to be able to rewrite these equations in terms of the same trig function with the same argument, and then we'll be applying techniques such as, for example, if there's denominators, we can multiply by the common denominator, that's both the left and the right-hand side of the equation, to clear the denominators. Okay, that's an algebraic technique. We can use factoring technique or the quadratic formula if we happen to have a quadratic. Okay, that would be an algebraic technique as well. Or we might make a substitution. This can be the case. We'll take a look at where this might be a case. This might work, for instance, for either one where we could use factoring or the quadratic formula, or this could be in order to change the arguments or the appearance of the arguments. I'll show you an example of each here in this section. And then finally, because of our use of identities, which may involve denominators that are where the denominator, of course, cannot equal 0 in any case, and where we are, the combination of using identities and the consequences of the algebraic techniques, we need to be on the lookout for the extraneous solutions. And extraneous solutions, again, are values of the variable that we get from applying correct techniques. So it's if we do all the math correctly, but we still get answers that actually aren't the correct answers. Okay, that's what extraneous means. If we did all the math correctly and we get an answer, but if we go and check the answer by plugging it back into the equation, it ends up not satisfying the original equation. Okay, so that happens for a variety of reasons. Okay, the main thing that we can do to protect against extraneous solutions is simply check the answers. As even if the work is done correctly, we still want to plug the answers back into the original equation, like, to see if it's correct. All right, let's just jump into some examples right now. There's not a lot of commonalities here. I tried to outline it. I would say if you can get the same trig function and the same argument, then you've got, it opens the door to all kinds of algebraic technique. Now let's just try some things out. First example I have is this: 2 cosine x minus 3 secant x is equal to -1. So with this equation, we recognize that we have more than one trigonometric function. All right? Okay, so we have terms with cosine x, we have a term with cosine x, and we have a term with a secant of x in it. Okay, so those are not the same trig function. They do, however, have the same argument. All right, so the argument in each case is x. Okay, so at least we have that established. Same argument, okay? But we have cosine here, we have secant here, okay? Right, so we have different trig functions, FCNS for functions there. Okay, so since we can't just factor this one like I did with the example earlier, then instead I'm going to use identities in order to rewrite all the terms in terms of the same trigonometric function. And in this case, the identity that we could use is a reciprocal identity. That the secant of x can be rewritten as 1 over the cosine of x. So let's do that. So then we have the equation rewritten as 2 cosine x minus 3. Well, let's write it like this. 3 times 1 over cosine x is equal to -1. Okay, and the other way that we could write that is to write 2 cosine x minus 3 over cosine x is equal to -1. Now, where do we go from here? Well, there's a denominator here that contains a variable in it. And so we would like to be able to clear out that denominator. We can do so by an algebraic technique, which is multiply by the least common denominator, right? So I'll make note that we started with a trigonometric technique here by using a reciprocal identity, and then we're going to apply an algebraic technique then to try to simplify the equation in the process of solving it. The LCD, okay, the LCD would be cosine x in this case, so we're going to multiply all terms by cosine x. Okay, so that means we're going to end up with 2 times the cosine squared x minus 3, because multiplying this by cosine x would just cancel the cosine x. And on the other side of the equation, we're going to have negative cosine x. Right? So what I did is I multiplied everything here by cosine x, and I multiplied this by cosine x as well, the LCD. So that cleared out the denominator. Now recall that a denominator cannot equal 0. Right? Because then we would have a term that is undefined. And if any of the terms here become undefined, then the whole equation becomes undefined. Okay? So this means that although we've eliminated the denominator, we still have to consider that any solutions we get from the resulting equation as we move ahead, any of the solutions to this equation might be extraneous. We might get values of x that it could turn out actually wouldn't have been available to us because they would have made this denominator 0. The thing we should do to protect against that is to make sure we check our answers. Whatever answers we get here, we should just go back to the original equation and check just to make sure that it actually works. All right, now from here, what do we do to solve this equation? Well, I'll notice now make note of the fact that we have the cosine that is squared, and we have another term that has a cosine that is not squared, and then we have a constant term, and that resembles a quadratic in form. If we move all the terms to one side of the equation and put this in descending order of the powers, we have 2 cosine squared x first, then we're going to have plus cosine x, right, which is cosine to the first power. And finally, we'll have minus 3, which doesn't include any cosines at all. And set that equal to 0. This is a quadratic in form equation. Quadratic in form. We can see that it is truly a quadratic. Right? If we wish to rewrite it this way, we can do a substitution. Like I'm going to choose a different variable that hasn't already been used. I do not want to choose x to do this because x already has a use in this equation. So I'm going to choose a different variable, and I'm going to choose u. If I let u equal cosine of x, okay, then u squared would equal cosine squared of x. Okay, that is an algebraic technique, the algebraic technique of substitution. We're making a substitution. By substituting then into this equation, okay, this term, 2 cosine squared x, would be written as 2u squared. The term plus cosine x would just be plus u, and then the minus 3 doesn't change at all, and then this is equal to 0. We now have a true quadratic equation, and we can try to solve this quadratic equation by algebraic technique, right? So more algebra. Those techniques could include factoring. If this is factorable, then we go ahead and factor it. And even if it wasn't factorable, we could use the quadratic formula, right? Which you could use the quadratic formula right now, whether it was factorable or not. In this case, I'm going to check to see if it does factor. If it does factor, okay, we should be able to find 2 numbers, integers that is, that multiply to equal the product of 2 and negative 3. 2 times negative 3 is negative 6, okay? And the linear factor, okay, the factor of this middle term here is 1. Can we find 2 integers that multiply to equal negative 6 but add up to equal 1? Now I'd say yes, we could choose 3 and negative 2. Okay. Right. Now we can use those 2 numbers to split the middle term up. This is a reminder of factoring strategy for a trinomial. We have 2u squared plus 3u minus 2u minus 3 is equal to 0. Now we can apply the technique, the factoring technique called factoring by grouping. We can group the first 2 terms and the second 2 terms separately from each other and find the greatest common factor of each term. The first 2 terms share a factor of u. We can take out the u. We're left with 2u plus 3. Now the next group, okay, the greatest common factor is 1, but because the leading term is negative, I'm going to take out the negative 1. Okay. If we take out negative 1, we are left with 2u plus 3, and that's what we were hoping to get left with, so that we have the same binomial in both of these groups. Okay. So we can factor out 2u plus 3 from both groups. The 2u plus 3 gets factored out, and that leaves us with u minus 1. Okay. In other words, 2u plus 3 times u minus 1. If you FOIL this out, okay, you can check by FOIL that if you FOIL this out, you should get back to this quadratic right here. If you are going to use the quadratic formula to solve this equation instead, okay, please be sure that you notice that we are solving for the variable u in this equation, not the original variable x. So if you do the quadratic formula, you would be doing u is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Not x is equal to this. X was the original variable that we have yet to get back to. Okay. So there is a cost to either of these strategies here, okay, an expense that we pay, and there's a benefit as well. Okay, and you have to weigh the cost and the benefit in order to find some way to solve the equation. We are solving for u right now. Okay, we set each of the factors now equal to 0. 2u plus 3 is equal to 0. U minus 1 is equal to 0. So over here we have u equals negative 3 halves, and here we have u equals 1. That's nice. Now we know what u is equal to. All right? All right, of course, what did we do? We set each factor equal to 0. That is an algebraic technique. Okay. Now what do? We want to go back to solving the original equation, which was in terms of x. And in order to solve that original equation, then let's go back to our substitution that we had selected. Let's see. Here was our substitution we had selected, that u equals cosine of x. Now we can use that substitution again so that we can then find out what this means about x. So u is equal to cosine x, and u is equal to negative 3/2. Therefore, cosine x, by substitution, is equal to negative 3/2. We'll take a look at that in a moment. And over here, this equation turns into cosine x is equal to 1. So we have these two trigonometric equations now for us to solve. And we want to find all solutions unless told otherwise. Okay? So I'm going to go ahead and find all solutions. Starting here, cosine x is equal to negative 3/2. If you went to your calculator, you could enter the arc cosine of negative 3/2. And if you try that right now, if you'd like to try that right now, see what you get. What message are you going to get on your calculator? Okay. Your calculator should give you some kind of an error message. And I want you to be familiar with which one it is your calculator gives you. Does it say error? Does it say domain error? Does it say not a number? What does your calculator tell you when you try to enter this in there? Because you're not going to get an answer to this one. Why are we not going to get an answer here? Well, remember that cosine, the cosine function, is always going to be between -1 and +1. Like, consider the graph, even if you wish. Right? Consider the graph of the cosine wave. It goes up and down and up and down and up and down. The highest, the maximum of the cosine function is 1, and the minimum of the cosine function is -1, unless we apply an amplitude modulation. But this is not amplified. There's no multiple in front. So the function itself, cosine, will never get to be negative 3/2 or negative 1.5. Negative 1.5 would be down here, right? And cosine never gets there. If you're using the unit circle's geometry, in the unit circle, we say cosine is the x-coordinate in the unit circle, right? Well, this is as far to the left as we can get in the unit circle, right? That point right there, the x-coordinate is -1. Over here, the x-coordinate is +1. The x-coordinate, that is, as we're moving on the unit circle, will never get to an x-coordinate of -1.5, but when we remain within the unit circle. So any way you look at it, this equation right here, the cosine x equals -3/2, that equation has no solution. The cosine of x cannot equal -3/2, right? No solution to that one. Okay, so that leaves us with solving the cosine of x is equal to 1. Using the geometry of the unit circle for this one, I'll go down here, for the unit circle, again, the cosine function is the x-coordinate of the terminal point in the unit circle. All right, as we travel around the unit circle, where is the x-coordinate going to equal 1? That's right here. Okay. And what value of the input? Okay. I know we're using x right here. We're talking about x-coordinate here. We're thinking this: the cosine of theta is equal to 1, or the cosine of t is equal to 1, maybe, if it's an angle or an arc length. We want to know what angle would be represented, okay, would be represented by a terminal point right here. Well, one value of the angle, okay, would be 0 degrees or 0 radians. I'm going to stick with radians for right now. Another value of an angle that would put us right there would be 2 pi. Another value would be -2 pi. And another one would be 4 pi, and another one is -4 pi, and there's many of these. There's an infinite amount of these. And if we combine all those into one set of solutions, that would be where theta is equal to any initial solution like 0, okay, plus integer multiples of the full period, so 2 pi k. Or in other words, just 2 pi times k, because 0 plus anything is just going to be the anything. So 2 pi k, where k is an element of the set of integers. Okay. Our equation was solving for x, so we have x is equal to 2 pi k, where k is an element of the set of integers. Okay. Some examples then of some some values that would satisfy this equation would be, well, x is equal to 0, okay? X is equal to 2 pi, x is equal to negative 2 pi, and more. Okay. Now let's check some of these solutions. Potential solutions right now. Okay, what if they're extraneous? Let's check to see if they actually work. So if we go back to the original equation right here, 2 cosine x minus 3 secant x equals negative 1, we can check values by plugging them into this equation. What we want to watch out for this particular equation is we don't want this denominator to equal 0. This denominator will equal 0 anytime that the cosine of x is equal to 0. Now, where is the cosine of x equal to 0? Using the geometry of the unit circle, cosine is equal to 0 if we are at this point or this point on the unit circle. That would be values like pi over 2 or 3 pi over 2. It would also include values like 5 pi over 2. It would include values like negative pi over 2, for example. But it's not going to include values right here. It's not going to include values like 0, 2 pi, negative 2 pi. Anytime we plug in any of those values that would make us terminate right there, the denominator would just equal 1. Right? In fact, that's how we solved it. We said we actually solved the equation a moment ago where the cosine of x would equal to 1. And as long as the cosine of x is equal to 1, this at least is not going to be undefined. It'll be equal to some defined value. Okay? But so the values that we want to exclude from here, okay, it doesn't look like they're showing up. Now let's just check a couple of our answers and see if they happen to work. 2 cosine x minus 3 secant x is equal to negative 1. All right, let's check a couple. Start with x is equal to 0. 2 times the cosine of 0 minus 3 times the secant of 0. Does that equal negative 1? All right, so question mark there. Are we asking the question, does this equal negative 1? Well, the cosine of 0 is equal to 1, so this is 2 times 1 minus 3 times the secant of 0, which is also equal to 1. It's the reciprocal of the cosine of 0. Okay, does this equal negative 1? Well, this would be 2 minus 3, and that does equal negative 1. So yes, so 0 is a solution to the original equation then. What about if we chose maybe 2 pi? If we chose 2 pi, let's plug that in. Cosine of 2 pi, secant of 2 pi. Okay? Well, the cosine of 2 pi is also equal to 1, and the secant of 2 pi again is equal to 1 as well. So we're still going to get a solution. In fact, any of the values that we choose from this list, okay, we're going to get that this equation is going to be true at those values. So we found all the solutions. Okay, so these equations can be, quite challenging then, okay, and they rely on our ability to, first of all, to be able to use identities and to know which identities to use. Here we only needed a basic reciprocal identity to apply to this one. And certainly it is requiring that we really understand the fundamental algebraic strategies that we had studied for solving algebraic type equations in order to be able to do the trigonometric equations. Okay, so here we had to use common denominators. We did a substitution. We did factoring as a strategy, right? Let's see. And also we had to check our answers for extraneous solutions. All of those steps are algebraic techniques. The trigonometric techniques included the use of an identity. Here we had a reciprocal identity, and being able to solve a trigonometric equation, which is the basis of what we did in section 6.1, solving basic trigonometric equations, using the underlying geometry to find the quadrants where we might find solutions, or the underlying geometry tells us when we wouldn't have a solution to a trigonometric equation, for example. Okay? And then using notions of symmetry, in this case like periodic symmetry, in order to express all solutions if needed. Okay. All right, so let's move on and try another example. Next example, solve the equation solve for solutions just in the interval, I'm going to switch to theta right now. I'm going to switch to theta, where theta is between 0 and 2 pi. Okay, so 0 is less than or equal to theta, which is less than 2 pi. Okay. And the equation is the sine of 2 theta minus the sine of theta is equal to 0. So with this one, first off, I want to say we should be a little bit careful here. Right? To solving this equation, we want to be careful to consider that 2 theta in the argument, right? We can't factor the 2 out. It's tempting to do that. It's tempting to try to say that this is 2 times the sine of theta minus sine theta is equal to 0, maybe. But that's not true, because that's not, right? We know that that's not true by looking at identities. In fact, the identity that we'd want to use here is the sine of 2 theta is equal to 2 sine theta cosine theta. That's the double angle identity, okay, for the sine function. Now, the reason we want to use that here is because the arguments are not the same as each other. Now, we have the same trigonometric function, right? We have sine and we have sine, right? So the terms have the same trigonometric function in them. That's good. Okay? But then if we look at the arguments, we have an argument of 2 theta versus an argument of theta. Okay? So here's a situation where we have different arguments. Okay? And at the top of the lecture, I said we want to have the same trig function and the same argument, ideally. Okay, we want to have the same trig function and the same argument, ideally. So, notice that if we use this identity here, we at least get the same argument, but then we have an extra trig function floating around, okay? But we can take a look, see what the equation is going to look like if we do that. 2 sine theta cosine theta, then, minus the sine of theta is equal to 0. Okay, so I'm going to factor out the greatest common factor. Okay. Factor out the greatest common factor is equal to the sine of theta. So this is sine theta times 2 cosine theta minus 1 equals 0. Then we set each factor equal to 0. Sine theta is equal to 0, and 2 cosine theta minus 1 is equal to 0. And solve each of these trigonometric equations for all their solutions, and we can check in the original equation. Sine of theta is equal to 0. Using the geometry of the unit circle, the sine of theta is associated with the y coordinate at every terminal point. The y coordinate would equal 0 at this point and at this point. And within the interval from 0 to 2 pi, which is where we're looking for our solutions right now, from 0 to 2 pi, not including the 2 pi, okay, that would give us solutions then where theta is equal to 0, that would be here, and where theta is equal to pi. Okay. Note that these solutions are in radians because we were asked up here to express solutions in this interval, and that interval implies that we are in radians and not degrees. Right? Just make a note up here. This is clearly an interval. Right? This is clearly an interval of radians and not degrees. So we're expected to find solutions here in radians, by the way the problem is stated. So 0 and pi are solutions to set this factor equal to 0. Now, the 2 cosine theta minus 1 equals 0. Okay, that's solving for cosine. We get cosine theta is equal to 1/2. Now, using the geometry of the unit circle, we say, well, the cosine of theta is the x-coordinate, and the x-coordinate is greater than 0 whenever we're in quadrant 1 or quadrant 4. All right, so we have a quadrant 1 solution, we have a quadrant 4 solution. So in quadrant 1, I'll call that one theta 1, and in quadrant 4, I'll call that solution theta 2. Now, we can use our our knowledge of angles versus outputs, like with a right triangle, if we want, right? Theta's right here. The adjacent side would be 1. The hypotenuse would be 2. Do we know what angular measure that is? Either in radians or degrees. Ultimately, we want the solution in radians. Right? That's one way that we can certainly do that, and I hope you do know that. So in this case, that would be a 60-degree angle, or pi over 3. So in this right triangle here, we would have pi over 3, 60 degrees, for that angle right there. Okay, so that's one solution then to this equation. In fact, that's also the reference number for both of these solutions. Okay. The other way that you could go about solving this equation, recall, is you can use the inverse trig function. If you did the arc cosine of 1/2, and if in your calculator, if you're set to radian mode, the answer you would get should be pi over 3. If you're in degree mode, the answer you should get would be 60 degrees. We should get the quadrant 1 solution by using the inverse trig function. In either case, we have that theta 1 is equal to pi over 3. That's a potential solution between 0 and 2 pi. And then we also need the quadrant 4 solution, right? Theta 2. Well, one quadrant 4 solution we could get would be negative pi over 3. But we don't want solutions that are negative. We only want solutions that are between 0 and 2 pi. Because that's what was requested of us. So we can find this solution for theta 2, and that can be found by taking 2 pi minus the reference number, which was pi over 3. And 2 pi minus pi over 3, all right, with a common denominator, that would be 6 pi over 3 minus pi over 3. That gives us 5 pi over 3. Okay. Great, so how many solutions do we have then? Okay, in the interval from 0 to 2 pi, the solutions we get, the set of solutions, I'll put them in the curly braces to list a set here, from lowest to highest, we have 0, then we have pi over 3, okay? Then we have pi, and then we have 5 pi over 3. That's 4 solutions, potentially, to the original equation. And let's check those solutions. Starting with theta is equal to 0. Okay. Oh, let's write down the original equation. So the original equation was the sine of 2 theta minus the sine of theta is equal to 0. Let's check theta is equal to 0. Then we would have the sine of 2 times 0 minus the sine of 0. Does that equal 0? Well, the sine of so 2 times 0 is 0, of course, and the sine of 0 is 0. And 0 minus 0 is equal to 0. Okay, so theta equals 0 is a solution. What about for pi over 3? Sine of 2 times pi over 3 minus the sine of pi over 3, does that equal 0? Okay, 2 pi over 3 would be quadrant 2. In quadrant 2, the sine is positive. Okay, the reference number is pi over 3. Okay? So in other words, the sine of 2 pi over 3, notice, is always exactly equal to the sine of pi over 3. Right? The y, in other words, the y coordinate here is the same as the y coordinate here, the same y coordinate as each other by symmetry. So whatever that's equal to, we know it's going to equal the sine of pi over 3. So this is going to equal 0. Now, what is it actually equal to, if that's more helpful, right? At pi over 3, the sine is square root of 3 over 2. So we have root 3 over 2 minus root 3 over 2, and that certainly does equal 0. I was just saying, more generally speaking, right, the sine in quadrant 1 and 2 with the same reference, they're always going to equal each other. So pi over 3 is a solution. What about theta is equal to pi? Then the equation would look like sine of 2 pi minus the sine of pi. Does that equal 0? Yes, because the sine of 2 pi is equal to 0, and the sine of pi is equal to 0. 0 minus 0 is equal to 0. And finally, what about 5 pi over 3? the sine of 2 times 5 pi over 3 minus the sine of 5 pi over 3. Does that equal 0? Well, 2 times 5 pi over 3 would be 10 pi over 3. Okay, and then we have minus the sine of 5 pi over 3. Does that equal 0? 10 pi over 3. Where is that? Okay, well, we know, by the way, we already know 5 pi over 3 is in quadrant 4. We found it to be there. Where's 10 pi over 3? Well, we have the top half of the unit circle is pi, goes out to pi by there, right? So that would be already 1, 2, 3 pi over 3. This is pi over 3, 2 pi over 3, 3 pi over 3. All right, continuing around, we'd be at 4 pi over 3, 5 pi over 3, and then 6 pi over 3, which is 2 pi, 7 pi over 3, 8 pi over 3, 9 pi over 3, 10 pi over 3. Okay, so this is where we're going to have 10 pi over 3. That would be right here. That's in quadrant 3. Okay. In quadrant 3, the sign is negative. Notice that also, of course, in quadrant 4, that's the sine of 5 pi over 3. There, the sign is also negative as well, right? Because it's the y coordinate. And by symmetry, these are always going to equal each other. The reference number is pi over 3. We just know it's going to be a negative output, okay? The sine of pi over 3 is, again, root 3 over 2. So the sine of 10 pi over 3 is negative root 3 over 2. So negative root 3 over 2 minus the sine of 5 pi over 3, which is also negative root 3 over 2. Okay? Negative times negative is positive, so this is in fact going to equal 0. We add these together. Okay? All right, again, these equations rely heavily on our previous understanding of the fundamentals here, not just of algebra, but also of trigonometry. Right? Okay, to be able to use these notions of geometry, reference, symmetry, understanding the definitions of the trigonometric functions, as well as the use of identities. Okay, so we have checked all 4 of these solutions. They all work. Very good. And so we found 4 solutions between 0 and 2 pi to the original equation right here. Okay, let's try another one. Solve again for, well, let's go to degrees. 0 degrees is less than or equal to theta, which is less than 360 degrees. Okay, let's do this one for degrees. 4 cosine squared theta plus 4 sine theta is equal to 5. Okay. So we have different trigonometric functions here. I was doing that in red before, right? We have a cosine here, but we have a sine here. Those are different. But the arguments are the same, at least, right? We have theta and we have theta, so those are the same, right? Same argument, right? But different trigonometric functions. So we need to use identities in order to get this in terms of just one trigonometric function, okay? Use an identity to get one trigonometric function. Should we get it all in terms of cosines or all in terms of sines, okay? All right. Consider the identities that we have available to us, right? I would choose to rewrite the cosine squared in terms of sines. Okay, that way we don't have to introduce like a square root or something like that. I'm talking about the Pythagorean identity. Cosine squared of theta is equal to 1 minus the sine squared of theta. That's from the Pythagorean identity, right? Which is the Pythagorean one is cosine squared plus sine squared equals 1. So cosine squared theta equals 1 minus sine squared theta. Substituting then into this equation for cosine squared of theta, okay, we get 4 times the quantity 1 minus sine squared theta. Then plus 4 sine theta is equal to 5. Now we have the same trigonometric function and the same argument. Okay, so now we're going to apply an algebraic technique to this. I'm going to start by expanding. It's distributing the 4. So 4 minus 4 sine squared theta, and then plus 4 sine theta, and then equals 5. And we have a quadratic. Notice, again, we have that quadratic in form type of an equation. We have sine squared, and we have sine that is not being squared here. Okay? So I'm going to want to get this in its standard form. That is, writing it in the order of terms from the highest exponent down to the lowest exponent in order. Negative 4 sine squared theta plus 4 sine theta, and then we have a plus 4, and then we're going to subtract the 5 in order to set this equal to 0. So negative 4 sine squared theta plus 4 sine theta minus 1 is equal to 0. Next thing I want to do is I would like to multiply by negative 1 because I don't want the leading coefficient to be negative. It can be, it's fine if it is, but it might be a little trickier to deal with the numbers. It's easier, in other words, it's easier to work with positive numbers than it is to work with negative numbers. So I'm going to multiply both sides by negative 1 to make the leading coefficient positive. Okay, so 4 sine squared theta minus 4 sine theta plus 1 is equal to 0. This is quadratic in form. So we can either do factoring strategy or we do the quadratic formula. Okay, so I'll check to see if factoring strategy works. Okay, 4 times 1 is 4, so that's the number up here, and negative 4 is a number down here. Okay, so question is, do we are there two integers that multiply to equal positive 4, but that would add up to equal negative 4? And I say, yes, there are two integers, negative 2 and negative 2. Right? Those multiply to equal positive 4, but would add up to equal negative 4. So we can split this middle term into two terms. So I'm going to write this as 4 sine squared theta minus 2 sine theta minus 2 sine theta again, plus 1 equals 0. And then I'm going to do factoring by grouping. Notice that I did not do a substitution in this case. Not because I can't, but because I just want to show you that it's possible to do it without a substitution. We could, in other words, if we want, let u equal to sine of theta. If u is equal to sine of theta, then we would write this equation right here as 4u squared minus 4u plus 1 equals 0. And then we could factor from there and continue as we did previously. Okay. I'm just showing, in this case, I'm showing how you can do the same process without having to do the substitution. But if you like the substitution approach, then I suggest that you try that on this example right now to see how you can attain the same solutions that I'm going to get to by doing it this way. So, common factor now. This group here, we're factoring by grouping at this point, this group of two terms has a common factor, greatest common factor of 2 sine theta. Take that out from these two, you are left with 2 sine theta minus 1. These two terms in this group, their greatest common factor is 1, but the leading term is negative. So I'm going to take out a negative 1, and that leaves us with a 2 sine theta minus 1. 2 sine theta minus 1, 2 sine theta minus 1, so we factor out 2 sine theta minus 1, and we're left with another 2 sine theta minus 1 after we factor out that common binomial there. Okay, so we have another 2 sine theta minus 1 equals 0. In other words, this is 2 sine theta minus 1 quantity squared is equal to 0, right? Because it's the same factor. So we don't have to set both of them equal to 0. Okay, there's only one factor here, so we set that equal to 0. So 2 sine theta minus 1 is equal to 0. So from this we have the sine of theta is equal to 1/2. Using the geometry of the unit circle, we have the sine, which is the y-coordinate, is equal to positive 1/2. The sine is going to be positive anytime we're in quadrant 1 or quadrant 2. Okay? So in quadrant 1, I'll call that solution theta 1. In quadrant 1, right, solution, I'll call it theta 1. And in quadrant 2, I'll call that solution theta 2. Okay. Now what is theta 1? Theta 1 can be found by taking the arc sine of 1/2, okay? Or by knowing the geometry of those triangles. What angle would be associated with a sine of 1/2? Okay, and that would be 30 degrees, or pi over 6. We said these answers would be in degrees for this exercise. So 30 degrees. That's the arc sine of 1/2. Okay? And that's also going to be the reference number, all right, the reference number in quadrant 2. So theta 2 is going to equal 180 degrees minus 30 degrees, which gives us 150 degrees. So our solutions are theta is equal to 30 degrees and 150 degrees. And you can check those solutions in the original equation, okay, to see that they work. Here's the original equation right here. Make sure you go and check to be sure, okay, that they're going to work. So 4 times cosine squared of 30 degrees, okay, plus 4 times the sine of 30 degrees, does that equal 5? Okay, so checking the work here. And let's see, so what's the cosine of 30 degrees? The cosine of 30 degrees, root 3 over 2. So this is 4 times root 3 over 2 squared, plus 4 times, now the sine of 30 degrees, as we said here, sine of 30 degrees is 1/2. Okay, root 3 over 2 squared is 3 over 4. So we have 4 times 3/4 plus 4 times 1/2, well that's 2. 4 times 3/4 is equal to 3, and 3 plus 2 does equal 5, so that's true. Okay, so that's the way you can check it. Check the 150 degrees, the cosine squared of 150 degrees, okay, and then 4 times the sine of 150 degrees, then does that sum equal to 5? 150 degrees, again, is in quadrant 2, okay, there we go. In quadrant 2, the cosine is negative. Okay, cosine of 150 degrees is going to be negative. In fact, the cosine of 150 degrees, okay, is negative. Is the negative counterpart to the cosine of 30 degrees. Okay, by symmetry. So cosine of 150 degrees is negative root 3 over 2. Well, the square of a negative number is going to be positive. All right, now the sine of 150 degrees is exactly the same as the sine of 30 degrees. In quadrant 2, the sine is positive. So the sine of 150 degrees is positive 1/2. Right, negative root 3 over 2 squared is also equal to 3/4, the same as positive root 3 over 2 squared was equal to 3/4. So we have 4 times 3/4 plus 2, and that equals 5 again. So yes, so we found the two solutions contained within the interval from 0 degrees to 360 degrees. Okay. 30 degrees and 150 degrees are those two solutions to the original equation here. All right, let's move on, try another example. How might we set up to solve this equation? Okay. Let's solve for theta is between 0 and 2 pi. Cosine of 2 theta plus cosine theta is equal to 0. The trig functions we have are both cosine, those are the same. But the arguments, we have 2 theta and theta, right? So we have different arguments here. And we want them to be the same arguments as each other, and we want the same trig functions if possible. We're going to use identity in order to do that. An identity. What identity can we use? If we can write cosine of 2 theta in terms of the cosine of theta, that would work. That's a cosine double angle identity. Remember, we have choices though for the double angle. Let's write out the 3 choices we have. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. That's a choice that we have. Another choice we have is 2 cosine squared theta minus 1. And a third choice we have is 1 minus 2 sine squared theta. Of these 3 choices we could choose, this, or this. Of those three, which one is most advantageous to us here? Given that the other term has a cosine in it, okay, I would focus on choosing then the one, right, the one of these three that only includes the cosine function. It's just going to make this easier to solve than the other choices would. Okay? Because we'll be able to get everything in terms of just one trigonometric function. So cosine 2 theta is 2 cosine squared theta minus 1. And then we continue with our plus cosine theta equals 0, right? So we did a substitution here with a double angle identity. And then we notice we have a quadratic in form. Okay, another one of these quadratic in form equations. So let's write it in the standard form, 2 cosine squared theta plus cosine theta minus 1 equals 0. And then let's go for factoring or the quadratic formula. Again, I'm going to go for factoring here. 2 times negative 1 is negative 2, and the linear coefficient is 1. What are two integers that multiply to negative 2 but add up to equal 1? That would be 2 and negative 1. So 2 cosine squared theta plus 2 cosine theta minus 1 cosine theta minus 1 equals 0. Solve that. Factor by grouping. First group, we can factor out 2 cosine theta, which leaves us with another cosine theta and plus 1. And in the second group, we factor out a negative 1, which leaves the factor cosine theta plus 1 again. Okay, and then it's equal to 0. Cosine theta plus 1 is the shared factor, and then the other factor is 2 cosine theta minus 1. 2 cosine theta minus 1. And that product then is equal to 0. Remember, you can check by FOIL, right, foiling this out to see that we would get back to this right here, the thing that we were trying to factor. Now set each of these equal to 0. Cosine theta equals negative 1 from this factor equal to 0, and cosine theta is equal to positive 1 divided by 2, 1/2. Okay, solve this one right here. Using the geometry of the unit circle to solve cosine theta is equal to negative 1. Okay, cosine is the x-coordinate in the unit circle, and that's equal to negative 1 at this point right here. The only value of theta then that we need is theta is equal to pi. That's the value of theta between 0 and 2 pi that would put us at this terminal point. And then cosine theta is equal to 1/2. We've seen that one already. In the unit circle, that's going to put us, because this is positive, that's going to put us in quadrant 1 or quadrant 4. In quadrant 1, I'll call that theta 1, and in quadrant 2, I'll call that theta 2. Okay, so theta 1 is going to be the arc cosine of 1/2. Okay, and the arc cosine of 1/2 is pi over 3, or 60 degrees. For theta 2, we could choose in general negative pi over 3, but we want our solutions now between 0 and 2 pi from the instructions. So we're going to take theta 2 to be 2 pi minus pi over 3, which would give us 5 pi over 3. Okay. All right, so theta 1 is pi over 3, theta 2 is 5 pi over 3. Okay, so our complete set of solutions for theta would be the set in ascending order. We would have pi over 3, then pi, and finally 5 pi over 3. Remember, you should check these solutions in the original equation to verify that they actually work. Okay, so let's take, for instance, pi over 3. Just a visual check now. If theta is pi over 3, then we're having the cosine of 2 pi over 3 plus the cosine of pi over 3 is equal to 0. Now 2 pi over 3 would be in quadrant 2, and pi over 3 is in quadrant 1. Notice that the cosine in quadrant 1, where it's positive, okay, is the same in magnitude, but negative in quadrant 2, right? So we have whatever the cosine of 2 pi over 3 is, okay, it's negative whatever the cosine of pi over 3 is. In other words, when you add these two x coordinates together, they're going to cancel each other out and you're going to get 0. Okay, so pi over 3 is going to work. Okay. Another value was pi. Right? The cosine of 2 pi plus the cosine of pi is equal to 0. Well, the cosine of 2 pi would equal 1, and the cosine of pi is equal to negative 1. And adding those two together, you would get 0. And then what about 5 pi over 3? So 5 pi over 3 would put us in quadrant 4. Okay. And then double that to get 10 pi over 3. Like we saw earlier, that would be in quadrant 3. Notice that in quadrant 4, the cosine is positive, but in quadrant 3, the cosine is negative. But they both have the same reference of pi over 3. Okay, so the x-coordinate here and here, right, we have whatever the x-coordinate is here, this is the same value but negative instead. So they're going to add together and equal 0. So by observation, I can tell these solutions are going to work. Okay, I urge you, though, to, in general, to check the solutions by plugging them in. Okay, that's the best way to verify that you actually found the correct solutions. Okay, let's try to solve another one in degrees. Solve for 0 degrees is less than or equal to x is less than 360 degrees. The equation, not x, I'll call theta. Let's do theta. The equation cosine theta over 2 plus the cosine of theta is equal to negative 1. So we have the same trigonometric function here of cosine, but different arguments. We have a theta over 2 and a theta. Okay, we have options here. One option, either way we have to use identity, by the way. One option, we can use the half angle identity. Cosine theta over 2, which is equal to, remember, plus or minus the square root of 1 plus the cosine theta over 2. That introduces a square root into this exercise, but it also introduces the plus minus, which is an issue of something we're going to have to deal with later in this exercise. We cannot ignore the plus minus. It does play an important role here, not just in the identity, but in the equation itself. It will make a difference. So we can do this substitution. It will get this in terms of just cosine theta. The other option that we have is to do a substitution here. And that substitution could be to choose another variable. Let's say I'll choose the variable x because it hasn't been used here. If I choose x is equal to theta over 2, so that this becomes cosine of x, okay, well then this theta right here, by that same substitution, that same theta, multiply both sides by 2, then theta is equal to 2x. This way we don't have any half angles. Instead I'll be using a double angle. And I'm going to go that route, because then I can avoid the square root issue and I can avoid the plus minus issue. That's my reasoning. So I'm going to go try that. If theta over 2 is equal to x, then this becomes cosine of x plus the cosine of 2x, and that's equal to negative 1. All right? So now we have a double angle here. All right? We have a double angle. And we want to get it in terms of cosine. So we're going to use the double angle identity for cosine that we used previously. 2 cosine squared x minus 1. Okay? So cosine x plus 2 cosine squared x minus 1 equals negative 1. Add 1 to both sides. You get this is equal to 0. So we have cosine x plus 2 cosine squared x is equal to 0. Now I'm going to use factoring strategy. Take out cosine x. So we have cosine x times 1 plus 2 cosine x equals 0. So either the cosine of x equals 0, or 1 plus 2 cosine x equals 0, which means cosine x is equal to negative 1 divided by 2. Now cosine x is equal to 0. On the unit circle, that would be when is the x-coordinate, in fact. The output of cosine is the x-coordinate here. When is the x-coordinate equal to 0 in the unit circle? That would be here and here, okay, which in degrees means that either x is equal to 90 degrees or x is equal to 270 degrees. Okay? And in the other equation, cosine x equals negative 1/2. Using the geometry of the unit circle there, cosine is negative if we are in quadrant 2 or quadrant 3. Okay? One solution here can be found by taking the arc cosine of negative 1/2. Okay, I'll call that solution x1. Okay, that's our quadrant 2 solution. We have x1. And then quadrant 3, the solution will be x, I'll call it x2. What's the arc cosine of negative 1/2? Okay, that would be this angle. Okay, this angle right here, which has a reference. Okay, a reference that is equal to 60 degrees. So this is going to be 120 degrees for that value of x. And x2, right? This means that the reference, by the way, this means the reference for x is equal to 60 degrees. So x2 is going to equal 180 degrees plus that 60 degrees, which gives us 240 degrees. So we now have 1, 2, 3, 4 values of x. But we're not done because the original equation was in terms of theta. X came from the substitution I had selected right here. We need to find now what is the value of theta. What is the value of theta for those given values of x? And then we want our solutions to be between 0 and 360. So since now theta equals 2 times x, okay, since theta is equal to 2 times x, right, then we have theta equals 2 times 90 degrees, which is 180 degrees. We have theta is equal to 2 times 270 degrees, which is equal to 540 degrees. We have theta is equal to 2 times 120 degrees. That gives us 240 degrees. And we have theta is equal to 2 times 240 degrees, which gives us 480 degrees. Okay? Remember that we want theta to be between 0 and 360 degrees. So of these solutions, which ones are between 0 and 360 degrees? So we have the 180 degrees is in that interval, and we have 240 degrees is in that interval. But notice that the 540 degrees and the 480 degrees are not in that interval. All right, so as much work as that was to do it that way, okay, in fact, I would expect this to be even a little bit more challenging if we tried it with the half angle identity, but still doable. We could solve it by using the half angle. Okay. It would give us a square root in there, and we would want to eliminate that square root. But more importantly, I think than that, well, that is important though, but also we're going to need to check our answers carefully because we're going to have to deal with this issue of plus minus. And I'm suggesting that substitution is going to be the better method to do this. Okay. So that you can avoid having to determine issues of quadrant and stuff there. Okay, well, we can take a look at it. Cosine theta over 2 plus cosine theta equals -1. Replace cosine theta over 2 with plus or minus 1 plus cosine theta over 2. And then plus cosine theta is equal to -1. Okay. Well, we could isolate the square root by moving this to the other side. Then we can square both sides. So we can square all of this, and we can square all of this. So squaring gets rid of the square root, and we're just going to have 1 plus cosine theta over 2. And on the right, we're going to have to FOIL. Okay, so we're going to do -1 minus cosine theta times -1 minus cosine theta. Okay, so that'll give us 1 plus 2 cosine theta plus cosine squared theta. So continuing from this point, I'm going to multiply both sides by 2. We have 1 plus cosine theta equals 2 plus 4 cosine theta plus 2 cosine squared theta. All right, so again, I'm multiplying both sides by 2 to cancel the common denominator. All right, now we have a quadratic equation. I'm going to combine all the terms on one side. I'll subtract then the 1 and the cosine theta from both sides. Okay. And then I'm going to write all the terms in the standard form. That's from the highest exponent, the highest power term, okay, down from there. So I'll have 0 on the left-hand side. The first term on the right-hand side will be 2 cosine squared theta. The next term will be plus 3 cosine theta, and then the last term, 2 minus 1, is 1. So now I'm going to go ahead and factor this quadratic. And I think first I'm going to make a substitution. I'm going to let u equal the cosine of theta, and then we can rewrite the equation as 0 equals 2u squared plus 3u plus 1. And that'll make it a little easier maybe to factor it. Results will be the same whether we did the substitution or not. It's up to you. Okay, so to factor, I'm looking for two numbers that multiply to equal 2, because 2 times 1 is 2. But the same two integers, they should be, that add up to 3, and that would be 2 and 1. So I can split the middle term up into a 2u plus 1u. Okay, and then we still have a 2u squared at the front, and we have a 1 at the end, still equal to 0, bringing all the terms down. And now we can factor by grouping. So the first group, we can take out a 2u, that leaves behind u plus 1, and the second group, the greatest common factor, is just 1, so we have 1 times u plus 1. Now the two groups share a factor of u plus 1, so that's one of the original factors. And the other factor is the remaining 2u plus 1. And we can check by foiling u plus 1 times 2u plus 1. You foil that out, collect the like terms, and you will find 2u squared plus 3u plus 1. You will get that back. It's a good idea to check it to make sure the factoring is correct. And now I'm going to set each of the factors equal to 0. U plus 1 equals 0, and 2u plus 1 equals 0. And then reverse the substitution to get back in terms of theta. So u was equal to cosine theta, so that means cosine theta plus 1 equals 0, and 2 cosine theta plus 1 equals 0. So that's reversing the same substitution we had selected. Now solving these two equations, we have cosine theta is equal to negative 1, and we have cosine theta is equal to negative 1/2. Okay, using the unit circle, and we can find where the solutions would exist. Cosine is equal to negative 1 when the x-coordinate is negative 1 on the unit circle. That happens here. And since we're in degrees, that means a solution is, or a potential solution right now, is where theta equals 180 degrees. So we'll check that solution to see that it works. For the other equation, cosine theta is equal to negative 1/2. Again, using the geometry of the unit circle, cosine, which is the x-coordinate, is negative in quadrant 2 and quadrant 3. So there's a quadrant 2 solution, let's call that theta 1. There's a quadrant 3 solution, and we'll call that theta 2. Both of those solutions have the same reference number associated with them. All right, let's take a closer look. So here's a unit circle. Okay, this angle right here, that can be theta 1. Then the remaining rotation back to the x-axis, that's our reference number, theta bar. And that's the same reference that we would have in quadrant 3, okay, when we're dealing with the quadrant 3 solution. Okay, here's the quadrant 3 solution that we're looking for in blue then. Okay, that's theta 2. Okay, what is the reference number? The reference number would be the arc cosine of positive 1/2. That would equal 60 degrees. Right? So that would be the acute angle, like in quadrant 1, such that the cosine of that angle is 1/2. Now, if you want to find theta 1 directly, because it's in a quadrant, right, which the arc cosine would output, if you take the arc cosine of negative 1/2, okay, you're going to get 120 degrees. That gives us our quadrant 2 solution. Recall that arc cosine always outputs an answer that is in quadrant 1 or quadrant 2. Every time you use the arc cosine, you'll either get a quadrant 1 or a quadrant 2 solution. But you would never get a quadrant 3 solution. Okay? So, although we can use the calculator to find the quadrant 2 solution, we still have to use our own notions of symmetry and geometry in order to determine the quadrant 3 solution. Right? That is, we can use the reference number. That's what I mean by symmetry and geometry. The reference number, which is 60 degrees, add that to 180 degrees because we're going to quadrant 3, and that's what gives us the 240 degrees, which is our third potential solution. Now we're not done yet because we have to check these solutions, okay, to see if they actually work. We'll start with the 180 degrees, and we're checking it in the original equation now, which was cosine of theta over 2 plus cosine theta equals -1. So let's plug in 180 degrees for theta. So the first term will be then the cosine of 90 degrees, and the second term is the cosine of 180 degrees. And we're checking to see if that sum will equal -1. Okay, 90 degrees and 180 degrees, if we check in the unit circle real quick, at 90 degrees the x-coordinate is 0, so the cosine of 90 is equal to 0. And at 180 degrees the x-coordinate is -1, so we have 0 plus -1, and that does equal -1. So therefore 180 degrees is a valid solution of the equation. Okay, now let's check the next potential solution of 120 degrees. So the cosine of theta over 2 plus cosine theta equals -1. Plug in 120 degrees for theta, we end up with cosine of 60 degrees plus the cosine of 120 degrees, and we're asking, does that equal -1? Back to the unit circle. 60 degrees is in quadrant 1, and the x-coordinate there is positive. That's positive 1/2. 120 degrees, right? Okay. The 120 degrees, that's in quadrant 2. Okay. It has the same reference number as the 60 did, but that cosine is going to be negative because it's in quadrant 2, so we get -1/2. But 1/2 minus 1/2 does not equal -1, right? 1/2 minus 1/2 in fact equals 0. 0 doesn't equal -1. So we tag the 120 degrees as incorrect. It is an extraneous solution. That is, we found the solution, we found this 120 degree potential solution by doing the math correctly, but when checking our answer, it actually was not a correct solution. Now, why did that happen? It has to do with, really back at the beginning, when we chose to do a half angle. By choosing the half angle identity, we have to remember that plus and minus is a possibility. And whether we remember it or not, the equation is going to remember it for us. That is, when we check our answer, right, we're going to find out that something went wrong. Well, this is the thing that we could say went wrong. We didn't make a mistake here. Okay? This is just something that happens. Okay? So we chose an identity that required a plus or a minus as a possibility to the output of this expression. But then we later squared both sides of the equation. And by squaring, that ended up getting rid of the plus minus, because the square of a positive is positive and the square of a negative is also positive. So we lost the information about the plus or minus possibility. And then we continued, after squaring, we continued with dealing with a quadratic equation, and we solved it correctly from there. Okay? I'll point out again, we did all the math correct. Even though we did all the math correct, we still ended up at a value of theta that was not a correct solution. Okay, so we have to strike the 120 degrees from our list of solutions. 120 degrees is not a solution to the equation. It was extraneous. Okay. Now 180 degrees was a solution to the equation, so it's not like we have no solutions. We have at least one. And we should check the other one too, the 240 degrees. So check theta equals 240 degrees in the equation. Cosine theta over 2 would be cosine of 120 degrees then plus cosine theta, which is cosine of 240 degrees. Let's check to see if that equals negative 1. Well, 120 degrees is quadrant 2 and 240 degrees is quadrant 3. In fact, both of them equal negative 1/2. So we have negative 1/2 plus negative 1/2. Okay, and those do in fact add up to equal negative 1, so that's correct. So 240 degrees was a correct solution. Okay. 180 degrees was a correct solution. Okay. So in the end, the true solutions that we found from 0 to 360 degrees, we found theta is equal to 180 degrees and theta is equal to 240 degrees. Those are the only solutions from 0 degrees to 360 degrees for the given equation. Okay. And those are the results we should keep. Okay, so when we did this one previously, we did so by using a substitution and then a double angle identity instead. Right, the substitution, we made x equal to theta over 2, which transformed cosine theta into a cosine of a double angle 2x. Then we used the double angle identity. Right? We used a double angle identity instead of the half angle identity in that case. We still had to check our solutions. At least we should check to see that we are within the interval that we want it to be. We want it to be from 0 to 360. When we used the double angle, we ended up with two other values of theta that we didn't want to keep because they were outside of that interval. Okay, so that was a price that we had to pay for using the double angle. When we used the half angle identity, there was a different price that we had to pay, and it was that it was more important that we really check our answers, not just to see that we did the math right, but that the answers that we got, even if the math was correct, that the answers themselves were also correct. Okay, so what we can take away from that is, one thing is, we don't necessarily know at the beginning of a process, okay, whether we're going to run into extraneous solutions or not. We don't necessarily know, for example, which identity we should use. Should I use double angle? Should I use half angle? I might say that in my experience, I'd prefer to use the double angle rather than the half angle. One of the reasons to potentially not use a half angle identity, if we have another option available, is that we have the square root in the half angle identity, which generally speaking creates more complex equations to solve than it would to use an equation that has, for instance, a whole number exponent like a square in it. The other is this plus minus issue, which is an issue of quadrant. All right, remember that it's not the quadrant of theta that determines plus or minus. It's the quadrant of half of theta that determines the plus or minus. And that's an extra complication that if we have the option to avoid, I would say we might want to just avoid it altogether. All right, as long as we have the option. So that's why I went through it first with the double angle. You might also notice that it took less space on the page, less work to do, seems like less effort too, just to use the double angle approach. Now, a lot of that, decisions about what should I do when going through a process comes from practice with a lot of examples and building an intuition. It's not necessarily a catalog of always do this and never do that, for example. So I urge you to try out different strategies on different exercises. Right? Even if you get the correct answers by doing it by one method, maybe try out a second method if you have the time, and decide for yourself which method you thought was better, maybe more robust, which methods are going to work on more solutions, okay, and ultimately save you time and energy in finding those solutions. And remember to always check your solutions, or at least to, until you build an intuition about when to be suspicious about certain solutions. You should certainly be checking your solutions, because these extraneous ones will show up even when all the math is correct. Okay. All right, so you have plenty to work on with strategies and using identities and solving these equations for this section. To try out the homework, feel free to contact the tutoring center for additional help. They're aware that you're working on this type of content right now and that it is challenging. And let me know as well if you have any questions. I'll be checking my email. Okay, take care.